So this is a continuation, chapter 8 again. For this, again, I think you might want a highlighter because I'm going to highlight a couple things. And then you are going to need that table that is on the front or the back of your shapes. This is going to be something we talk about today. So you may want to have that out while we discuss this. So covalent bonds, because they are the sharing of electrons, we need to talk about the fact that electrons might not be shared equally. So we are going to be talking about a big concept called polarity, okay? And please note this only pertains to covalent bonds. That really doesn't affect you guys because that's all we're dealing with in here. But if you had ionic bonds, those don't have polarity in them. So I always define polarity this way by doing the non versus polar. So non-polar bonds are where the electrons are shared equally, okay? So they would be anything that has the same atoms, O2, N2, and the one we're going to focus on a lot is going to be the carbon to carbon bond in these organic molecules. So those are where electrons are being shared equally. So they are considered non-polar, so they're not pulling one way or the other. When they are not shared equally, that is where we have most of our bonds. So anything like water, HCl, you have two different atoms attached. You have some difference there on the what we call the pull on the electrons. The ones we're going to look at, especially with carbon, is carbon with oxygen, or carbons with, say, the halogens like Cl. You're going to have a difference of how the electrons are pulling. Well, why are the electrons not being shared equally? Well, it has to do something with electronegativity, okay? And that's a topic that you may have learned first year chemistry. Different atoms have different pulls on electrons. So we have what we call electronegativity table, which is this table here. It's only the first two columns of the periodic table, so these are the first two, and these are the last five. It does not include noble gases because noble gases don't want any electrons. So this is based on the Pauling scale. You don't need to know that, but the bigger the number, the more pull it has on the electrons, meaning it wants the electron closer to it because it's going to satisfy the octet a little bit better. So what you will find is things are on the right-hand side. So fluorine is the most electronegative element. So as you go from left to right, you get bigger and bigger numbers. The lower electronegativity numbers means you have less pull on the electrons, okay? So how does this relate to anything or what we're talking about? So if I take water, for instance, and I look up its electronegativities, oxygen is 3.4, hydrogen happens to be 2.1. Okay, so if I look at the bond itself between oxygen and hydrogen, okay, the bond itself, because again, we could draw it over here in the bench shape. Oxygen, because it has the bigger number, means the electrons are closer to it. So if we were to draw the dots, they would be closer to oxygen than hydrogen. But because dots are kind of a pain to kind of deal with, we're going to be drawing something called a dipole arrow. And the dipole arrow is always going to be pointing towards the one with the bigger number. So since oxygen is the 3.5, we're going to point that arrow towards it. And we're going to do a little slash mark on the end. Okay, so this is called a dipole arrow. Okay, and the reason for that is because both of those electrons are closer to oxygen, this is slightly negative, so that's like a little lowercase delta, and this is a lowercase delta positive. So the hydrogen end is slightly positive, this side is slightly negative. It is not a full +1 or a -1, it's just a slight change. So if I were to look at my molecule here, I would see that the dipole arrows would be pointing towards the oxygen, okay, being a bench shape. Well, when we're looking at electronegativities, what we're going to be doing is taking the two numbers and finding what we call the difference. So if I take 3.5 and subtract 2.1, I get a difference of 1.4. So we are going to say that if the difference between those two numbers in the bond itself is between 0 and 0.4. We're going to consider that to be non-polar, okay? Even though you have some difference between the two, you could say that there's probably not going to be that big of a difference. If it is between 0.5 and 1.9, it's going to be considered polar. So since this is 1.4, we are going to consider this to be a polar bond. So we're going to say that the bond between oxygen and hydrogen is a polar bond. And then if we get anywhere above that, what's happening is the electrons are being pulled so tightly to one atom versus the other, they actually do a transfer. And again, we're not going to deal with that because we're not going to have any ionic bonds in this class. So on the next page, we can easily see with HCl, okay, that Cl has a higher number than the hydrogen. And again, this top table, you will always be given to use, all right? This bottom table, you're gonna have to memorize these ranges. So really, you have to memorize 0.5. That's really kind of the cutoff for a polar bond. That's really the only number you need to pay attention to. So since chlorine has the bigger number, my dipole arrow is pointing towards the chlorine, okay? And again, this slash mark, okay, can be thought of as like a plus sign, since the hydrogen is slightly positive and the chlorine is slightly negative because the chlorine has pulled those electrons towards it. When you take the difference between the two as 0.9, you then determine if it's a polar bond or not, okay? So that is what I have in your notes here, and it is on the bottom of that table. So that's always going to be how we determine if the bond is polar or not. But really, not going to spend any time on that more than that, because really the big question mark is the molecule polar? Not just the bond itself, but the molecule itself. So polar bonds are always going to be determined by the electronegativity difference. Boom, okay? Subtract the two numbers, see if they are greater than 0.5. That's it. If we're talking about the molecule itself, the shape has to be polar, okay? And what this means is the molecule itself, one end is positive while the opposite end is negative, okay? So if we think of like a water molecule, you're gonna have one side that is negative, one side that is positive because of that shape, okay? And again, a dipole means not just the dipole arrow, but the dipole means that the molecule has a positive and a negative charge on it. Okay, so let's start the conversation here with this example. Okay, so CH4 is a tetrahedral. Okay, so the first thing we have to look at is a tetrahedral shape.